Okay, so welcome back again to another video. In this video, we are going to talk more about the retrosynthesis analysis, and here we are going to start talking about the 1,5-dicarbonyl compound structures, right? In this case, we have talked much about retrosynthesis analysis. If you want to continue with our video series, we have talked about the introduction, 1,3-dicarbonyl compounds, and disconnection methods, functional group interconversions. Likewise, we have talked much. So here you will find our video series. I will put the link here. You can watch it if you haven't had the basics regarding this retrosynthesis analysis, right? So why we are calling 1,5-dicarbonyl compounds, because if we position this one here, number 1, you will see the other carbonyl compound occurs at the fifth carbon, right? 1,5-dicarbonyl compounds. Before we are moving into the disconnection part, I want you to understand the synthesis of this dicarbonyl compounds, right? So basically it's the Michael addition reactions. We have talked a very detailed mechanism about the Michael addition, so you can watch it here. I will give you a quick overview. Let's say we have two compounds like this, okay, here, and let's say we have another compound like this. Okay, so you know this is acidic, so you can form a nucleophile here. So this nucleophile can form resonance structures like this. Okay. Now you will obtain a compound like this. So we have talked about detailed mechanism about this, right? I'm just recapping this. If you want to know about the detailed mechanism, I highly recommend you to go to this link. We have talked about it very detailed wise and full mechanism. So here I am just recapping this, right? So here just like this, you know, this is a nucleophile, so this can attack other compounds by facilitating of this lone pair, right? So this will go back to form the pi bond between oxygen and carbon. This will go and attack to this particular place, okay, and this will go here and this will go here. Now you have a double bond here. I will take another color. You will have the double bond here and you will have a lone pair here. If you introduce a acidic medium or just water, maybe this double bond can go and attack to this water by the facilitation of the forming double bond between the oxygen and carbon. So this is the basic idea about what happening in the Michael addition. You will see now after this you can form the 1,5. Here this carbon and this carbon is going to form a bond. Okay. You will form the 1,5-dicarbonyl compounds here. Okay. If I number the structure, is let's say this is 1, this is 2, this is 3, this is 4, and this is 5, like this. 1, 2, 3, 4, and 5. Here's the basic mechanism. So let's move on with our retrosynthesis analysis. I will remove this. So again, like if you want to know about the Michael addition detailed wise more clearly, I highly recommend you to go to that video. We have talked the Michael addition mechanism very clearly in this particular video. I'm just recapping it again. Now when you are trying to introduce a disconnection for the 1,5-dicarbonyl compounds, right, you need to introduce it through here or here, right? Because like you need two compounds, you need two molecules as the synthons. One should contain this structure, this double bond structure, and other one should contain the nucleophile structure like this. So this can go and attack to this place, this can move on to here and here, like the Michael addition can take place, right? You need to form the Michael addition from the synthon. So in order to place that, you need this product and you need this product. So you need to arrange your disconnection to facilitate the Michael addition, right? So let's see how we can do it. For this particular reagent, for this particular example, okay, when we try to introduce the disconnection, let's say we have two possible bonds, either here or here. First one is through here, right? First one is through here. Let's say we have gone through this one. Okay, and we have gone through that disconnection, we have obtained it like this: CO2 ET, and here we have the plus charge here. This is the synthone, and here we have the OD. Okay, this is the synthones we get. But always remember, right, when it comes to the disconnection, this particular carbocation, this is not possible, right? Because this is alpha beta unsaturated carbocation. It's not possible. It's not possible. Okay, so this kind of structure won't that much available, so this is not a very good disconnection. So our disconnection should be through here, right? Through here. Like if you think about again, like if you can't understand that specific point, you can think it like this. You can see here we have a carbon and a carbon, and here you can see this is also a carbon and carbon, right? If you disconnect through here, okay, and you will give the positive charge here and you will give the negative charge here, you will see this is more negatively facilitated because two carbonyl compounds. If you we have talked about the Maronic esters also. Maronic esters also. If you remember about the Maronic esters, you will see that when the alpha carbon is in between the two carbonyl compounds, the nucleophilicity of this is very much high. So this particular disconnection is much more feasible than this. So this is wrong completely. Okay, you need to go through the disconnection. So you will have this particular structure. You have you have the negative charge here, okay, and you will have ODP, and this is the positive charge. Now when you introduce the synthetic equivalence, right? Synthetic equivalence for this particular molecule is the Michael addition product, right? If you remember. Now we are going to introduce the Michael addition, right? Synthetic equivalence for this particular molecule is same. Just ignore the lone pair. Now what happened is, okay, this is a nucleophile now. This will go and attack to here, and this will shift here. This will shift here with a suitable positive proton. This double bond, the newly formed double bond, will go and attack to proton. This will come back to form the carbonyl compound. I'm okay. I think you are okay with it. With this particular reaction, we can obtain the target molecule. Okay. So I hope it's fine up to now, right? So another question you may think, like, why can't this particular position attack to this part? This is also acidic, right? But if you look closely, this is more acidic than here. This is more nucleophilic than here, because now this position here, you will see it is in between two carbonyl compounds, two carbonyl carbons. So this is much more acidic, and this much more feasible. That's why the reaction will go through this place other than this one. Okay, I hope it's okay. Now let's move on. Okay, so let's look at another example. This is a very little bit tricky example. I want you to work on this before I am going to explain it. So here, this is your target molecule. You need to introduce a retrosynthesis analysis, and the question was told that one of the last reagents should be this compound, right? Now you should stick to this pathway. You have to think about obtaining this particular compound by disconnecting this target molecule. Okay, now let's look at what we can do. Okay, now first you will see we have few patterns. One thing which I can see is alpha beta unsaturation here. This is a carbonyl group, alpha carbon and beta carbon. Alpha beta is unsaturated, so you can go with that particular disconnection. Or there is 1,3 dicarbonyl compound structure. You can go with that particular disconnection. But you will see that your compound here, look at your compound, look at your reagent which you have to obtain. Do you see any similarities? Here this compound is just like same here, right? Okay. Just like same here. If you choose to disconnect with 1,3 dicarbonyl compounds, you will destroy this compound. You won't be able to obtain this particular reagents clearly. So what I'm going to do is I'm going to leave the 1,3-dicarbonyl structure and I'm going to focus more on this alpha beta unsaturation. You can directly disconnect this, or otherwise you can do a functional group interconversion to convert this into a alcohol. I mean, like attaching a OH group here like this. Over here I have attached a OH group. We have talked about why we can't attach a OH group in here, right? Normally we don't do that because it will get destabilize the compound. We have talked about in alpha beta unsaturated structures. Okay, now we have this. Now we can disconnect to this bond to obtain. I will directly go with the synthetic equivalence, right? I think you are now familiar with the syntones and stuff. Here we have the pH. Now the synthetic equivalence, you will see this is a positive charge now. OH with positive charge, it will go with the ketone structure, and here we have the pH. This is just like the same. Here you can see this is a alpha carbon, so this has a initial acidity with the proper base, with the proper basic medium. You can remove one of the protons and leave a lone pair which can act as a nucleophile. Now this is my compound. Now let's see what I can do. Okay, now you may see a structure like this. We can do a disconnection through here, right? Here, 1 2 3 4 5 1,5-dicarbonyl structure. Yes, there is 1,3-dicarbonyl structure too, but if you go with this type of disconnection, you will lose this reagent, right? That's why I have told you that you need to stick to this particular pathway. Now when I go to disconnect through this way, I can achieve two reagents. One is this with a double bond here. Here we have a pH plus. I have directly gone with the synthetic equivalence, right? I hope it's fine with the syntones. Here we have the OET structure. Now these are the two final reagents, right? Here we have achieved this particular reagent here, and the other reagent is this one. So this is the particular two reagents which we want to synthesize this particular target molecule. This is a very interesting reaction. You may heard of this. This is the Robinson annulation, right? Robinson annulation. So when we go for the synthesis, okay, we have two reagents, which is one is this one, and the other one is this one. Okay, when you add in this medium, when you add ETOH, ethanol, okay, you can obtain our target molecule. This is a one step, not a one step reaction, I mean like this is a very simple reaction, okay, which is we call as Robinson annulation. Here we have the pH here, we have the pH here, we have double bond here. So this is the reaction. Okay, if you see this kind of like I hope you now understand how we can approach for a 1,5-dicarbonyl structure, right? So when you have a question like this, like when they have specified into a particular path, you need to stick with it, right? Because it has a reason, right? You can do a disconnection here, and obtain a few reagents, but this is a well-known acceptable mechanism, very acceptable reaction. This is one. So that's why you have to go with this pathway. A disconnection through here is possible, but when it comes to availability of this kind of mechanism, this kind of pathway, this connection cannot be approved. This is the only way. I hope you got the idea which I'm trying to explain, right? So this is the 1-5 diagonal structure. I hope it's okay to you. If you have any question, feel free to comment below. I will try my best to help you in this journey. Thank you, and check out our other videos. We have talked much about the organic synthesis and biochemistry, kinetics and stuff. Check out our playlist. We have a lot of content.